So today's task is to review, hopefully thoroughly, for our next class, which is test number 2. I realize that that might not be the case for people watching on cable TV. It might also not be the case for people that watch this later on DVD. So what I would urge you to do, those folks, is pay attention to the pacing guide that's provided for you so that you can make sure if your test covers this same material or not. Our test in here for this group of students is Monday. Today's Friday. And it covers 2.8. 8th section of Chapter 2 up to and including 3.7, which we finished up yesterday. There is a section that we deleted in there. I believe it's 3.3. Does that sound right? It's got some applications that really are not appropriate for folks that take this class. Yes, 3.3 we did not cover. So that is not included on this test. So I heard as we were kind of talking before the cameras started rolling that WebAssign questions, maybe a couple of those we can look at. I've kind of summarized each section. We can do that, and then I've got an old test here that we started to look at questions from that yesterday. We can go ahead with that too. So I have a pretty good feeling about your mastery of the material, but still I want you to, prepare beyond where you are today. But I don't think anybody is so far behind that test 2 is just not going to be a good situation for you. I can kind of sense by facial expressions and by your responses that all of you are in pretty good shape. What was that WebAssign? Y to the X?
X to the Y equals Y to the X.
Okay. And that's what question number in WebAssign?
16.
16. So the equation is Y to the X. Just looking at that, what thought process comes to mind? And actually, a couple should come to mind.
Natural.
Okay, taking the natural log of both sides, logarithmic differentiation, and what else? Implicit differentiation. So it's Y to the X equals X to the Y, and we want Y prime, so we want dy over dx. So if we take the natural log of both sides, what advantage do we gain by taking the natural log of both sides?
Bring down the exponent.
Okay, this comes out in front. That is an exponent property. A log is a power, and when you have a power of something raised to a power, you can multiply the powers. So that's what we're going to do. X natural log y equals y natural log x. Is that all right? We haven't taken the derivative yet, so all this is preliminary. Are we at a position now where we can take the derivative?
Yes.
Okay. So we want to derive implicitly. We don't want to solve for y. Don't even know if, in fact, that's possible. So we've got a product here and a product over here. So we're product rule both sides. We've got all kind of rules going on here. First, times derivative of natural log y with respect to x plus natural log y times derivative of x with respect to x. It's kind of a waste of space there. Product on the other side first times derivative of natural log with respect to x plus natural log of x times derivative of y with respect to x. Does that sound right?
Yes.
We haven't taken the derivative yet. We've kind of set it up. What's the derivative of natural log of y with respect to x?
1 over y dy dx.
Good. So it's the natural log of something variable. So the derivative is 1 over that something times the derivative of that something. Natural log of y times derivative of x with respect to x. Looks like 1 to me. Derivative of natural log of x with respect to x.
1 over
1 over x. If it bothers you that that's different from this over here, it's really the same. It's 1 over x, derivative of x with respect to x, which is 1, so we typically don't write that. And here, this answers itself. What's the derivative of y with respect to x?
dy dx.
It's dy over dx. What's the task now?
Get all the dy dx on one
Okay.
side. And
All the dy over dx terms on one side and everything that doesn't have that on the other side. So this looks like x over y, dy over dx. If we bring this term over, it is positive over here, so it's negative if we bring it over. This term does not have dy over dx in it, so we send it to the other side. Term that stays over here is y over x. The term that comes over here is minus natural log y. Does that look correct?
Mm-hmm.
I think I've moved things properly, but isn't necessarily always the case. So we would factor out dy over dx, which leaves x over y minus natural log x and divide through by that quantity that is being multiplied by dy over dx. That and that knock out, so we're left with that complex fraction. We've got fractions within fractions. So we might want to resolve that. That might be a version that WebAssign would take.
Probably.
Maybe not.
Mm.
So if we wanted to get rid of the complex fractions, what could we multiply by? What would get rid of the fraction in the numerator? Multiplying everything by x?
Yeah.
If we do that to the numerator, we have to do that to the denominator. What would get rid of the fraction in the denominator? Multiplied by y. So if we're going to get rid of fractions, we better multiply top and bottom by xy. So what would that look like?
xy squared.
Don't the x's drop out here
Yeah.
on the
Oh,
first term?
y
I'm going to
squared.
take that, distribute it to both pieces. This, distribute it to both pieces. So xy times y over x is what? Y squared?
Y squared, yeah. Minus x ln y.
xy,
ln.
natural log y.
Yeah.
It's probably a little bit better than the numerator before we did that. And xy times x over y would be
X squared minus xy ln x.
I don't know. I would probably try that as my final answer. Did anybody successfully get that one to go?
I put in
You
the
got it,
first-
Casey? This one?
I
Work.
think that's what I got.
Or this version right here before we...
That one didn't work.
That one didn't work,
That's the one that I put in.
Yeah, that's what I got.
and it did work?
No, the
This
bottom.
one. Okay, and it did work.
Mhm.
Okay. Actually, they both should work, so I don't know why this version,
I hope that
which is
doesn't work.
100% equivalent to this, why it doesn't work, but maybe it doesn't like the fractions within the fractions.
Could be.
Anything, any further issue with this one? Is that a fair test question? Probably a little bit tougher, a little more time-consuming than a test question. But the concepts covered are certainly going to be covered on the test. Logarithmic differentiation. If you've got a variable in the base and a variable in the exponent, be prepared to do that. Implicit differentiation, where you're deriving a non-x term with respect to x, you have to accommodate that. And then what else did we use here? Product rule, right? All the test will certainly have those items on it. Anything else from web assigned before we leave that?
Yeah, there was trying to find it.
While you're looking, the one question that came up before class started was the ninth derivative. It says find them, I guess, y9. I'm not exactly
It's
sure.
d9 over dx9.
Oh,
like
okay.
d
So
to
it
the
does.
ninth
It uses the ninth derivative of y with respect to x all 9 times. Okay.
There's no y there.
Okay. So the ninth derivative of whatever the function is. If you haven't done this, I think if you'll take the first derivative and then the second derivative and the third derivative, that might be enough. You got that answer right. Did you just see a pattern?
Yeah. Well,
How far did you have to go to see the pattern?
I mean, it just kind of makes sense that it would make a pattern. I
Right.
don't know. I didn't really write anything out.
Okay. If you, this might be enough. If you don't see it when you get the third derivative, I think you'll see it by the time you get to the fourth derivative. And then you can kind of see what would happen. Now, these look a little cumbersome when you get here and here, but try to think about what would happen if we continued to find the derivative all the way out to the ninth derivative. Some terms will disappear because you're eventually going to take the derivative of a number with respect to x, and that's 0. Therefore, the whole product is 0. So this is a pattern problem. That ninth derivative problem is a pattern problem. Certainly don't find the ninth derivative. See a pattern. Hopefully here, but if not here, I think you'll see it by that point in time. Catherine, did you find another one?
It's number 11.
Yes.
And the question says, use logarithmic differentiation to find the derivative of a function.
Okay.
The function is y equals the square root of x, exp, so e raised to the x squared.
So square root of x is a
Times.
Okay.
Yeah, exp x squared times.
So e to the x squared.
Yeah, and then parentheses x squared plus 1 to the 10th power.
X squared
Yeah, plus 1
Plus 1.
to the 10th power.
to the 10th.
Uh-huh.
So product of 3 things.
Yeah.
Okay. I think, didn't we develop a 3-term product rule in here?
I think.
You don't have to remember that.
Yeah, we
but,
did something.
but it is the product of 3 quantities. I guess with log differentiation, that's not going to matter. So we would take the natural log of both sides.
Can't you plus them all or make them
Yes.
all? Okay, good.
Yeah.
Okay.
I'm just trying to show that in
Yeah.
2 separate steps. So I'm sure most of you will probably have shorter versions of what I actually write out in class, and that's fine. So the advantage on the right side, there are multiple advantages. When we have a product of things and we take the natural log of that product, it becomes what? Addition. Now, how do you remember that? Why does that, how does that fit in with mathematical rules in general? When you multiply things that have like bases, which we are going to convert them to a base E problem, right? What do you do with their exponents?
Adding them.
You add the exponents. That's all we're doing, is we're adding a bunch of exponents. We're going to add 3 exponents. That is an exponent. That is an exponent. and that is an exponent. So it's not a little trick. It's a sound mathematical principle. You want to multiply things that have like bases, you add their exponents. Anything else that can be done on the right side?
Exponents can come out front.
Okay. Natural log of the square root of x is really natural log of x to the 1/2, and that 1/2 can come out in front. Natural log of e to the x squared. That's just x squared, right? And then you could say there's a natural log of e there, but what is the natural log of e? That's 1. So another way to think of that is the natural log is the power you would raise e to get that. It answers itself. What power would you raise e to get e to the x squared? You'd raise it to the x squared. And here we could bring the 10 out in front. Now don't make the mistake of saying the natural log of a sum is the sum of the natural logs, because it is not. You cannot distribute that natural log to these two pieces. The natural log of a product is the sum of the natural logs. The natural log of a sum cannot be simplified. Everybody okay with that
Yes.
step, that stage? We ready to take the derivative? Okay, derivative of the left side is what? Half is a coefficient. Derivative of natural log of x with respect to x. Derivative of x squared with respect to x.
2x.
10 is a coefficient. Derivative of the natural log of x squared plus 1 with respect to x. Good. Times 2x, right? Derivative of the inside function. Everybody okay with that?
Yes.
This, to me, would be a fair test question. I don't think this is too... I mean, you probably are not going to write down this step anyway. You're probably going to skip that. And you may, in fact, even skip right down to this step right here. Several of you would probably start here. So it's not a real cumbersome problem. Multiply both sides by y. So y times 1 over y. So there's a 1 over 2x. There's a 2x. And what, a 20x? So that is a correct version of the answer, but it probably would want us to put in the original y value since we want a derivative with respect to x. So what is y equal to? It's this stuff up here. Remind me when we're done with class to talk about next week's schedule, since we've got kind of a strange week with fall break coming up.
No
I don't see any reason that we would ever have to get a common denominator and put all these terms together. I don't think anything's going to be gained by doing that.
So how do you know, like, I think the reason I didn't know how to do this was because I tried to do it as doing x squared and e to the x squared as just a product, without doing logarithmic differentiation.
Yeah, well,
how
I
are
would,
you supposed to know?
I would,
when it's appropriate
if it
to
gets
use
real
it?
ugly, like this is pretty ugly with 3 terms and a square root and something to the 10th power. If it doesn't say that we want to differentiate logarithmically, I would kind of be leaning that direction.
Okay.
But if it doesn't say that and you want to use, product rule, if you wanted to start this with the product rule, somehow you would probably want to put 2 of these together. Like there's the first term of the product, there's the second term of the product, and start that way. This is kinder.
Yeah.
This is easier, less cumbersome. The answer is probably as simple, maybe even simpler, even though it looks bad. That's just the original y value, so it makes it look worse.
So,
Go ahead.
On the test, are you going to tell us
Yeah,
if we have to
test.
use logarithms
Yes.
or not?
Yeah,
Okay.
because I want to see, there'll be a problem, I hope it'll be evident anyway.
Okay.
The type problem that I would give you is not going to have another way to solve it. So it'd be something like this. It would be y equals x to the sine of x. And you're not going to have another way to solve that except logarithmic differentiation.
Okay.
Anything else from WebAssign?
The second derivative of one of them. Hold on.
I have that up here.
Second
I
derivative.
think you're talking about.
Okay, what was the
which one are you
first derivative? I
talking
can't
about?
remember. What number was that?
I
Number
think
10.
you're talking about 10.
10.
I think
Yeah.
so, yeah.
Yeah, I have it up on my computer right now.
Okay, what's it say?
The original function is the natural log of the quantity secant x plus tangent x.
Yeah. I think you just have to simplify it.
And what's it?
It wants
that's-
the first derivative and then the second.
That's what y is
Yeah.
equal to?
Yes.
Yeah.
Okay, so y equals that. And it wants the,
First derivative and the second derivative.
okay.
I have the first derivative up here. If everybody got the
Well,
first one.
actually, this is probably a good problem to look at because of what happens when you derive the inside function. And we'll see this problem eventually, in, if not this course, the next course, in reverse. So the first derivative, we've got the natural log of something. The derivative of the natural log of something is what?
1 over.
1 over that.
Itself times the derivative of that stuff.
Times the derivative of that stuff. Again, that's a step you probably won't write down, just writing it down because I'm trying to make it just a little bit easier to follow. So we need to derive the secant.
Secant x times tangent x.
Plus derivative of tangent of x
Secant
is
squared x.
secant squared. So I hope it's going to come up before we stop class today. But derive, I mean, you've got to be prepared to derive sine, cosine, tangent, secant, cosecant, and cotangent, all of them. Okay, the kind of the basic 6 trig functions. Be prepared to derive any of those.
What about the inverses? Or is that good?
2 inverses. The inverse sine, which is probably the lesser important of the 2, but in the inverse tangent, we're going to see that a lot.
Okay.
So
But
those are the 2.
Be able to derive them, like in what sense?
Well, use them. In other words,
Okay.
if I had an inverse tangent of x, and I ask you, that was in a problem, and it asks you to find the derivative of that, either have that memorized or
Right.
be prepared to do a little work on the side.
Okay, so we don't have to show you how to
No,
get that
no.
answer. We know what it is.
Unless you forget it, then you want to
Okay.
go back to the way of deriving that. Do you see anything that can be gained here by simplification?
Take out a secant.
Good. In the numerator, they both have a secant. If you factor it out of there, it leaves tangent plus secant. If you didn't see this, by the way, it's going to make the second derivative
Yeah,
kind of
that's
bad.
why.
That's what I did wrong. That's why I couldn't get
And
it.
then it's just cancel out.
Now, do you see a like term, numerator and denominator?
Tangent, secant.
Tangent plus secant is the same thing as
Yeah.
secant plus tangent, right? Because addition is commutative, so the order doesn't matter. So this thing and this thing reduce. So the first derivative is really just secant,
Oh my god.
which makes the second derivative a whole lot easier.
I derived that whole thing.
Girl.
So, but did it simplify to secant tangent, the other one, or did it accept the whole?
Oh,
agreement?
it accepted
It
the whole
accepted-
thing.
Okay. So the derivative, if that's the first derivative, then the second derivative should be what?
Secant x tangent x.
Secant tangent. So the fact that this
I
numerator
haven't found the second derivative like that.
factored, you will see that again. That this is a kind of a purposeful problem. Now, let me set up this problem that I know we're going to see later on. So if we know the derivative is the secant. So that's kind of eventually what we're going to start with. We're going to start with the derivative, and the derivative is the secant. Do you know what the original function is before we took its derivative?
No.
There it is. So that is the antiderivative of the secant function. We just found the derivative of this function and got secant. So the antiderivative, we're not there yet, but we'll get there. The antiderivative of secant is this function. So you'll see that again. All right. Let's take it section by section. Talk about what it is you need to know, and then kind of give a general overview, and maybe take a problem or two from this test that was given last spring. So if you are given the function, this is section 2.8. We did a little bit of this prior to 2.8 as well. If you're given the function, can you graph its derivative? Or if you are given the derivative, can you graph the original function? So kind of how do you go back and forth from a function to its derivative or the other direction? And some things that I'll actually write these down when we get to section 2.9. Derivative is 0. What's that mean? Derivative is undefined. What does that mean? Derivative is positive. What does that mean? Derivative is negative. What does that mean? And then basically throw that list in reverse, and you've got it to work for the other direction. So facts about the function, how does it translate to the derivative? Facts about the derivative, how does that translate to the original function?
Where can we find your old test at? What's the website?
It's on the syllabus, I think.
It's on the syllabus.
Awesome. Oh, you mentioned that. Thank you.
Another thing that's mentioned in 2.8 is if a function is differentiable, which means you can find its derivative, then that function is continuous. So if you can find its derivative, it's continuous there. Is the converse of this true?
No.
It is not true. Can you yourself come up with a counterexample of a function that is continuous but not differentiable?
Absolute value.
Absolute value.
Absolute value? Anything that has what? A cusp or corner or any abrupt change in direction. So here's a function right there that is continuous, but it is not differentiable at this place right here.
What do you do if there's like an absolute value in a problem? Do you just treat it like if it's the absolute value of x, like in some sort of derivative?
Yeah, you have to go back to the definition of absolute value is explained kind of left of the origin, right of the origin. So everybody knows what it looks like, but the definition, absolute value of x is in fact x if x is greater than or equal to 0, right? If you have a 0 or any positive number, isn't the absolute value of that positive number itself? And if the number is negative, so you have -3. What do you do to -3 to end up with +3?
Make it positive.
You negate it.
Yeah.
So really, absolute value consists of two lines defined over a different part of the domain. So if you wanted the slope of the this part right here, what's the slope of the tangent lines here?
1/1.
What's the derivative
One.
of x?
One.
1. Okay, and the other part So you kind of have to break it down into its constituent pieces according to the definition. What's the slope over here? Negative 1. So that's how you deal with absolute
But
value.
if that was in a problem with like absolute value of x over x,
Yeah.
like something else, like if you were doing like the quotient rule and you had to use absolute value,
Yeah,
like that was in a homework, I think,
It was, and I couldn't
and I didn't know
figure
it
it
was.
out.
I just didn't.
We
get
don't
it.
have we
I
don't
used
have a
positive.
way to differentiate absolute value. So you would have to split that up into two problems based on the different ways in which the absolute value is defined.
So based
So-
on x and negative x.
Yes.
Okay.
For one time through that problem, I would replace absolute value with x itself, and the other time through that problem, I would replace absolute value of x with negative x.
Okay.
Now, if it also said something in the problem that x is greater than 0 or x is greater than or equal to 0, that says you can replace absolute value of x with x
I
itself.
think that's what it says in the problem.
Okay.
I'll have to go back
Yeah,
over
it's
it.
with the
But it-
positive.
it-
or-
There is no way to derive absolute value. You have to kind of split it out into its whichever piece is relevant to that problem. Now, we're going to also do problems later that have to do with an area under a curve. So we maybe would want the area under here and then the area all the way out to here. Again, we're going to have to split that up into two distinctly different curves. This curve is a very different curve from this one. So we would split that problem into two parts. Again, based on the definition of absolute value.
And that's going to come later.
Yes.
Okay.
2.9. What does the derivative say about the function? So we're kind of going derivative to function. So if we know that the derivative is 0, what does that say? And I'm hoping that as we go through this, this is stuff you're saying as we look at it, I know this. I know everything about this. That's a good sign. If all this looks new to you, that's not a good sign today, since we have a test over all this stuff on Monday. So if the derivative is 0, what's that say about the original function?
It's like
Horizontal tangent line there, so
Yeah.
it's kind of instantaneously flat there. So we have a horizontal tangent line. If the derivative is undefined, for our purposes, what does that say about f? Vertical tangent line, or it's very steep at that point, about as steep as you can get. If the derivative is positive, what's that say about the original function? It's increasing from left to right. We read a graph like we read a page of prose. We read it from left to right. And if the derivative is negative, decreasing. So if we're finding the critical points, that's where we find the critical points, right? And those are points that are probably more important than just knowing it's increasing there and decreasing there. Where it's flat and where it's instantaneously as steep as it can get, those are points pretty appropriately named critical points. So we can find relative max and relative minimum values by talking about these kinds of points. If it's flat at a certain point, and we know it increases into there, gets flatter as it comes in, leaves here fairly flat but decreases, we know that point is at least a relative max. We have a place where we know the curve is flat, the derivative is 0, it decreases into here and increases out of here, then we've got a relative min. But just because it does those things does not guarantee that it's one or the other. So we have a place where the curve is flat. It might increase into here, and it might, in fact, increase out of it. So that is not a relative max, not a relative min, We could test that beyond with the second derivative and see that this is concave down and this piece is concave up. So this point is a
Point of
point of
inflection.
inflection. But it is not a relative max, not a relative min. Okay, what does the second derivative say about the original function? What if the second derivative is 0 or the second derivative is undefined? Those give us possible what?
Changes in concavity.
Changes in concavity, and if it does change concavity there, these are
Inflection.
points of inflection. So these are possible points of inflection. And we really don't know if, in fact, they are points of inflection until we see what happens on either side of them. If there is a legitimate change in concavity, there, at that specific point, then it is a point of inflection.
Thank you.
What else? Second derivative, positive. What's that mean about the original function?
Concave up.
Concave up. And second derivative, negative. What's that tell us about the original function?
Concave down.
Concave down. So separate those ideas in your mind, and we're going to continue to use those in this course beyond this test. First derivative information is flat, steep, increasing, decreasing. Second derivative information is
Concavity.
possible points of inflection. Why? Because this is concavity. Concave up and concave down based on the sign, SIGN sign of the second derivative.
Do we have a calculator tomorrow? I mean, on Monday, on our test.
Oh, yeah. Yeah, now if the problem, as is the case with this whole course, if the problem asks you to graph, then your graphing mode of your calculator is off limits on that problem. So you'd have to justify it with stuff like this. You'd just have to say, well, the first derivative is 0 there, the first derivative is undefined, and graph it based on the calculus that you've learned in this class rather than punching a button on your calculator. Chapter 3, derivatives of polynomials, and I'm hoping this is very, very much review, and exponential functions, as well as other things. So we decided that the derivative of x to the n with respect to x, what's that kind of power rule, exponent rule shortcut?
N times x. N minus 1.
Yep, we've used that hundreds of times already. The derivative of a constant times a function
0.
with respect to x, we're allowed to bring that constant, which is really a coefficient, right, along for the ride, and then take the derivative of the function itself. This is first presented in this section, but authors don't really address it till later in Chapter 3, but we've also covered that. The derivative of a to the x, where a could be 2 or 3 or 5, or in fact the number e, but if it's kind of not known what it is, what's the derivative of a to the x? Okay, a to the x, because it's not a natural exponential function, that's the one that carries with it a little extra baggage. There's the extra baggage. And the derivative of e to the x, which fits into this, is e to the x. And you could say natural log of e, but there's no reason to say natural log of e because that's 1. I'm just going to write down what was in Section 2. We've done plenty of those. Just to remind you that these are things you need to know. What is the derivative of a product, and what's the derivative of a quotient? So I'm hoping that those are pretty much locked in today. 3.3 we did not do, which was mentioned earlier. 3.4 is the derivative of our trig functions with respect to x. So if you've got sine, cosine, tangent, or their reciprocals. Reciprocal of sine is what? Cosecant. Reciprocal of cosine is secant. Reciprocal of tangent is cotangent. So all 6 of the basic trig functions know those derivatives. Let's just mention them. Derivative of sine is?
Cosine.
Derivative of cosine is?
Negative sine.
Okay, and those kind of work in pairs, right? Sine and cosine, kind of remember those in pairs. Derivative of secant is secant times tangent. Derivative of cosecant is negative cosecant times cotangent. So again, these two can kind of be remembered in pairs. And then these two, derivative of tangent is
Secant squared
secant
x.
squared. Derivative of cotangent
Negative
is
cosecant.
negative cosecant squared. So you're kind of learning the function and its co-function as a pair. There are some patterns there. Excuse me. Chain rule. We had 3 kind of good versions of that. It might be kind of an extended power rule. So you've got this inside function that is raised to a power. So the derivative would be, as the power rule would have us do. Now that's where the power rule stops, but then the new piece, according to the chain rule, is what?
Derivative of the inside.
Derivative of the inside function. That's one way to think of it, an extended power rule. You might have y in term, you might have y in terms of u and u in terms of x. If that's the case, you can think of the chain rule as deriving y with respect to u and multiplying that by derivative of u with respect to x. So that's another version that's presented of the chain rule. The last version that's presented in this text, and you can kind of latch on to whichever of the 3 makes the most sense to you. Maybe all 3 make sense and they kind of complement one another. If we have the derivative of a composed function which is really the derivative of the f of the g of x. We take the derivative of the outside function, which the outside function is the f function, so it's f prime evaluated for g of x, and you would follow that up with the derivative of the inside function. So they all 3 say the same thing. Whichever one kind of speaks the loudest to you, hang on to that one, but you should get at the same destination, whichever method. Jonathan?
And in theory, you also take the derivative of x inside of it.
Right.
Say that was
If
x
this
plus
is
1.
not just x, if it's a function of x, you would continue to derive until you get to the kind of the innermost function inside. Also addressed in this section were parametric. So if you have y as some function of t and x as some function of t, y in terms of t, x in terms of t, and you want derivative of y with respect to x, you could find derivative of y with respect to t, put it in the numerator. Derivative of x with respect to t, put it in the denominator. You can kind of see the dt's knocking each other out here, or if you multiplied the top by dt and multiplied the bottom by dt, can't actually do that because this is a separate entity. But this time, instead of their product, you actually take their quotient if they're in terms of the same variable.
And that would be equal to 1.
That is what we
No, dy dx.
want here. That's dy over dx. 6, section 6. We had implicit differentiation. So don't necessarily solve it for y in terms of x. If you've got x's and y's all in the same equation, just derive it as it is and solve for dy over dx. Also in this section, we had orthogonal trajectories, two sets of curves or family of curves such that where they meet, the slopes of the tangent lines are negative reciprocals of each other. So if you find the derivative of one family of curves and you get, let's say, a over b, for the other family of curves, the slopes better be negative b over a, right? If the slopes are negative reciprocals of each other, then the curves represented by those derivatives, that family of curves, they are mutually perpendicular, or they are called orthogonal trajectories. So you would find the derivative of one set of curves, find the derivative of the other set of curves, show that they are negative reciprocals. We will revisit that later, but that's kind of the first look at orthogonal trajectories. Inverse trig, and I mentioned a few minutes ago, derivative of the inverse sine and derivative of the inverse tangent is all you're responsible for at this point in time. The 7th section, which is our last one for this test, derivative of logs. So if we have log to the base a of x, its derivative is 1 over x. Extra baggage in the denominator this time. You have natural log of x, just 1 over x. Now, all of these have a chain rule that goes along with them. For example, if you have the natural log of u, where u is some function of x, it's the same basic idea, except instead of 1 over x, it's 1 over u, whatever that variable quantity is. And then you would have to finish that up with a chain rule component derivative of u with respect to x. And also logarithmic differentiation. Take the natural log of both sides, then simplify hopefully before you take the derivative, but after you take the natural log of both sides, then take the derivative. And we've actually done a couple problems today with logarithmic differentiation. All right, we're out of time. See you on Monday, and we will take a test.
How many problems?